reduce the likelihood that fatal strikes on humpback whales may occur. And this study is from 2010 by Harris and colleagues that found that whale activity around cruise ships is actually quite high in some areas. And the figure depicts two scenarios. One where the speed of the cruise ship was less than 13 knots, and one at which the speed was more than 13 knots. And the areas, the colored areas are depicting whale activity, the number of whale surfacing events around the ship. As you can see, for a 1 kilometer path, there's many more whale surfacing events around the ship that's going faster. And this gives an indication that vessel speed is an important factor that determines the probability of encountering a whale. In fact, the study that we're conducting here in Hawaii using our whale watch fleet as a vessel of opportunity yielded very similar results on this point, that speed is important. So have many of the studies that have been conducted on this problem. And I will talk a little bit more about our study later on during the presentation. But here is some other interesting data that is available that kind of brings home the point and sort of quantifies a little bit the effects of speed. In a 2007 paper, Vanderlaan and Taggart suggested, based on elementary momentum theory considerations, so modeling basically, that the fate of a whale in a ship strike is a function of both vessel speed and whale mass and the impact that results from these collisions. So the data that are presented here in this graph assume that the mass of the vessel represented in the data is much greater than that of the whale struck. Okay, so we are talking about large tonnage ship. These researchers estimated that the probability of a lethal injury to a whale as a function of vessel speed as at the time of vessel collision varies along that curve that you see there. So the statistically determined function, which is the solid line in the graph, estimates the probability that a lethal injury to the whale occurs. And the other two curves surrounding are the 95% confidence interval, so the variability in the data. So this simple logistic regression model that they used shows that the greatest rate of change, which is shown by the slope of the curve, that area in the middle with the different colors. So the greatest rate of change in the probability of having a lethal injury on the part of the whale occurs between a speed of 8.6 knots and 15 knots. In fact, at 8.6 knots, the probability of a lethal injury is about 21%, and at 15 knots is about 79%. Everything above 15 knots pretty much results in 100% lethality for the whales, so whale death for sure, according to this model. Of course, there's a lot of uncertainty around these data because of the variability that is inherent with all data sets. But at least this study has a very elegant way of showing us that speed does matter, and we need to take that into account. Another interesting study attempted to model what happens to a whale when it's found in the path of a boat. There are forces that act upon the whale that are beyond just the speed of the boat. There's a lot of suction associated with the movement of the boat in front of the whale that sort of contribute to the impact force, to this acceleration force that the whale kind of experiences when directly in front the path of a whale, the path of a boat, sorry. So what they found using a scale model of both a ship and a whale in an experimental tank is that the acceleration experienced by the whale with increasing speed, kind of it's linear and increases very much with ship speed. And the graph depicted in figure A shows what happens when the modeling occurred by keeping the whale at the surface. This is one circumstance in which the most likely outcome is the whale to be impaled by the bulb of the ship, and the impact at strike basically kills the whale depending on the speed, again, of the boat. The second scenario is that of where the whale is swimming below the surface at about twice the draft of the boat. In this particular scenario, it's not so much the ship hitting the whale directly, but more the suction of the ship's track sucking the whale underneath the boat and into the propeller. And this is when most propeller injuries are more likely to occur. So this is a kind of another nice study, but of course, a model is a model, and a model is as good as it gets, but it's missing some important elements here. It's missing the whale behavior, is missing the reaction of the boat, and particular circumstances that may surround a specific event. But it gives us some clues of what may happen. Here are some examples also when we know that speed is important. And we have heard some examples already of how successfully some of these options have been adopted, for example, in Massachusetts. Limiting speed may be a viable option in certain particular areas, but may not be in others. This is an example of what happened what could happen when you change things slightly. So this is, again, Vanderlaan and Taggart that calculated the speed reduction without moving the shipping lanes in Canadian waters to reduce, again, collisions with whales. And basically, a reduction in speed by keeping the shipping lanes in that particular area would have resulted in a 52% reduction in overall risk. But if you look at it from the perspective of the commercial operations, the transit time by the ships in that particular area would have increased by 20%, which is probably not a good option because not only that ship would have spent more time in that area and probably ran into more whales, but also that was very not cost effective for shipping companies, especially if we had perishable goods on board and transit time was increased that much. The other option, rerouting, was calculated to provide a 62% reduction in overall risk, but only a 1.4% reduction in the time of the transiting ships. And so this kind of is just to bring the point that not all solutions fit all areas and all populations, and that the local environment needs to be studied and evaluated to figure out what to do. Another example of a struggle in this particular area of shipping lanes is happening in the Santa Barbara Channel with blue whales. Blue whales are distributed worldwide with 4 recognized subspecies and 5 potential subpopulations in the North Pacific. And blue whale stocks have been severely depleted by commercial whaling, with the North Pacific post-whaling blue whale stock estimated at only about 1,400 animals. The good news is that this stock is replenishing and the number of whales is increasing, and specifically the California coast seems to be a very good environment for blue whales lately. and both because of a change in blue whale distribution and probably an overall increase in the population. So recently, the abundance of blue whales in the eastern North Pacific was estimated at approximately 2,500 animals, still pretty low for this population. So on the coast of California, in the Santa Barbara Channel, we have those bright red shipping lanes that kind of bisect the channel, very narrow place, and the dots, the squares that you see is the area of distribution of feeding blue whales that are attracted by the good feeding conditions along the California coast in the late summer, early fall. And as you can see, unfortunately, the distribution of the whales and that of the shipping lane and the presence of the shipping lanes are overlapping. And there's still a lot of debate about what to do. So this is an area where there might have to be different types of decision made. This data is from Cascadia Research Collective in collaboration with Scripps and funded by many other agencies along the California coast as well. I'm stuck. Sorry. So for a vessel operator to avoid a collision with a whale, first the whale must be detected, and then the operator must maneuver to avoid collision. In the case of a large ship, this may not be the case, may not be possible, especially at low speed, because these large ships are not very maneuverable. And success is very much dependent on the operator's ability to also predict the movement of the whales once they are detected. But what about all these small vessels and medium-sized vessels? Their movement may be much more erratic